1. Machine learning, logistic regression. Logistic regression, a classification algorithm. Logistic regression is a statistical model used for classification tasks in machine learning. It's a popular technique used to predict the probability of a binary outcome, example yes/no, true/false. How does logistic regression work? Linear combination. The model first calculates a linear combination of the input features, x, and their corresponding weights, w. Z equals W0 plus W1x1 plus W2x2 plus Wn asterisk xn. Sigmoid function. The result of the linear combination is then passed through a sigmoid function, also known as a logistic function. P, y equals 1x, equals 1/1 plus e caret, z. The sigmoid function maps any real-valued input to a value between 0 and 1, representing the probability of the positive class. Prediction. If the predicted probability is greater than a threshold, typically 0.5, the instance is classified as belonging to the positive class, otherwise, it's classified as belonging to the negative class. Applications of logistic regression. Email spam filtering, classifying emails as spam or not spam. Customer churn prediction, predicting whether a customer will churn or remain with a company. Medical diagnosis, predicting the presence or absence of a disease. Credit risk assessment, assessing the risk of default for loan applicants. Advantages of logistic regression. Interpretability. The coefficients in the model can be interpreted to understand the importance of each feature in the prediction. Efficiency. Logistic regression is computationally efficient, making it suitable for large datasets. Robustness. It can handle both numerical and categorical features. Disadvantages of logistic regression. Nonlinear relationships. Logistic regression assumes a linear relationship between the features and the log odds of the outcome. If the relationship is nonlinear, the model's performance may suffer. Multi-class classification. While logistic regression can be extended to handle multi-class classification problems, it's generally less efficient than other algorithms like support vector machines or neural networks for these tasks. Logistic regression is a fundamental algorithm in machine learning for binary classification problems. Here's a brief overview. Logistic regression predicts a binary output, 0 or 1, yes or no, etc., based on one or more input features. Uses a logistic function, sigmoid, to model the probability of the positive class. Goal: find the best fitting logistic curve that separates classes. Mathematical formulation. P equals 1/1 plus e caret, z. Z equals W0 plus W1x1 plus W2x2 plus Wnxn. P, probability of positive class. W, weights or coefficients. X, input features. Assumptions. Binary output variable. Independence. Linearity in the log odds. No multicollinearity. Evaluation metrics. Accuracy. Precision. Recall. F1 score. ROC AUC, receiver operating characteristic area under curve. Python libraries for logistic regression. Scikit-learn, sklearn.linear_model.logistic regression. Stats models, statsmodels.discrete_model.logit. Important considerations. Feature scaling and normalization. Regularization techniques, L1, L2, to prevent overfitting. Model interpretation and coefficient analysis. Remember, logistic regression is a powerful tool for binary classification, but it's essential to carefully evaluate assumptions, select relevant features, and avoid overfitting. 2. Machine learning, grid search. Grid search is a hyperparameter tuning technique in machine learning. Here's a brief overview. Grid search exhaustively searches for the optimal combination of hyperparameters. Evaluates a model's performance for each combination. Goal: find the best hyperparameters that result in the best model performance. How grid search works. 1. Define a grid of hyperparameters to search. 2. Train a model for each combination of hyperparameters. 3. Evaluate the model's performance using a validation set. 4. Select the combination with the best performance. Advantages: simple to implement. Exhaustive search ensures optimal hyperparameters. Disadvantages: computationally expensive. Time-consuming for large grids or complex models. Python libraries for grid search. Scikit-learn, sklearn.model_selection.gridsearch.cv. TensorFlow, tf.keras.wrappers.scikit_learn.keras classifier, with grid search CV. Best practices: use a random grid search for large hyperparameter spaces. Use cross-validation to evaluate performance. Monitor performance metrics and adjust the grid accordingly. Remember, grid search is a powerful technique for hyperparameter tuning, but it can be computationally expensive. Use it wisely. 3. Pre-processing, categorical data. Pre-processing categorical data in machine learning. Categorical data, which represents discrete categories or groups, often requires specific pre-processing techniques before being used in machine learning models. Here are some common methods. 1. One-hot encoding. Process: create a new binary column for each unique category. Assign a 1 to the corresponding column if the instance belongs to that category, and a 0 otherwise. Example: if a category has 3 values, A, B, C, create 3 new columns, A, B, and C. An instance with category B would be represented as 0, 1, 0. When to use: when the categories are mutually exclusive, an instance can belong to only one category. 2. Label encoding. Process: assign a unique integer to each category. Example: if a category has 3 values, A, B, C, assign 0 to A, 1 to B, and 2 to C. When to use: when the categories have an inherent order, example low, medium, high. However, be cautious as some algorithms might interpret this as a numerical relationship. 3. Frequency encoding. Process: replace each category with its frequency in the dataset. Example: if A appears 5 times and B appears 10 times, replace A with 5 and B with 10. When to use: when the frequency of categories is informative, example rare categories might be less important. 4. Target encoding. Process: replace categories with the mean target value for instances belonging to that category. Example: if the target variable is price and category A has an average price of 100, replace A with 100. When to use: when the target variable is continuous and the categories are predictive of the target. 5. Count encoding. Process: replace categories with the number of times they appear in the current dataset. Example: if A appears 3 times in the current batch, replace A with 3. When to use: when the frequency of categories in the current dataset is relevant. 6. Binning. Process: combine categories into fewer, larger bins. Example: combine categories A, B, and C into a single bin ABC. When to use: when the number of categories is too large or when there are many rare categories. Choosing the right technique depends on the specific characteristics of the data and the machine learning algorithm being used. For example, one-hot encoding is often suitable for tree-based models, while label encoding might be preferred for linear models. For machine learning, K-means. K-means is a popular unsupervised learning algorithm for clustering data. Here's a brief overview. K-means partitions data into K clusters based on similarities. Each cluster has a centroid, mean point. Goal: minimize the sum of squared distances between points and centroids. How K-means works. 1. Initialize K centroids randomly. 2. Assign each data point to the closest centroid. 3. Update centroids as the mean of assigned points. 4. Repeat steps 2 to 3 until convergence. Key concepts. Centroids, mean points representing each cluster. Clusters, groups of similar data points. Distance metrics, Euclidean, Manhattan, etc. Python libraries for K-means. Scikit-learn, sklearn.cluster.kmeans. SciPy, scipy.cluster.vq.kmeans. Evaluation metrics. Silhouette coefficient. Kolinsky-Hurabaz index. Davies-Bolden index. Best practices. Choose the optimal number of clusters, K, using elbow method or silhouette analysis. Use feature scaling to ensure equal importance of features. Avoid using K-means for high-dimensional data or non-spherical clusters. Remember, K-means is a simple yet powerful algorithm for clustering data, but it requires careful parameter tuning and evaluation. 5. Machine learning, bootstrap aggregation, bagging. Bootstrap aggregation, commonly known as bagging, is an ensemble learning technique used in machine learning to improve the stability and accuracy of models. It is particularly useful for reducing variance and helping prevent overfitting, especially for high-variance models like decision trees. Key concepts of bagging. Bootstrap sampling. Bagging involves generating multiple subsets of data from the original dataset using bootstrap sampling. Bootstrap sampling is a technique where datasets are created by randomly sampling with replacement. This means some data points may appear more than once in a subset, while others may not appear at all. Model training on each subset. For each bootstrap sample, a separate model, often of the same type, example decision trees, is trained. This leads to the creation of multiple models that may capture different patterns in the data. Aggregation. Once all the models are trained, their predictions are aggregated to form a final prediction. The type of aggregation depends on the task. For classification, the predictions are combined using a majority vote. For regression, the predictions are combined by averaging the outputs of the models. Why bagging works? Variance reduction. Since bagging trains multiple models on different subsets of the data, it helps reduce the variance of the final model. This is particularly helpful for models that are prone to high variance, like decision trees, leading to more robust predictions. Combating overfitting. By training on different samples and aggregating the results, bagging smooths out the noise that individual models might pick up on, which helps reduce overfitting. Example algorithm, random forest. Random forest is a well-known implementation of bagging, where decision trees are used as the base models. In addition to bootstrapping, random forest introduces another level of randomness by selecting a random subset of features at each split in the decision trees. Applications of bagging. Decision trees, especially with random forest. K-nearest neighbors. Support vector machines. Bagging is highly effective when dealing with high-variance models but is less beneficial for low-variance models like linear regression. 6. Machine learning, cross-validation. Cross-validation is a technique used in machine learning to evaluate the performance of a model on unseen data and prevent overfitting. It involves splitting the dataset into multiple folds, training the model on a subset of folds, and evaluating its performance on the remaining fold. This process is repeated multiple times, rotating the folds, to get a more robust estimate of the model's performance. Types of cross-validation. K-fold cross-validation. The dataset is divided into K equal-sized folds. The model is trained K times, each time using K1 folds for training and the remaining fold for testing. The final performance is calculated as the average of the K-test set evaluations. Stratified K-fold cross-validation. Similar to K-fold, but ensures that each fold maintains the same class distribution as the original dataset. Useful when dealing with imbalanced datasets. Leave one out cross-validation, LOOCV. A special case of K-fold where K equals the number of data points. Each data point is used as a test set once. Computationally expensive for large datasets. Repeated K-fold cross-validation. The K-fold cross-validation process is repeated multiple times with different random splits. Provides a more stable estimate of performance. Benefits of cross-validation. Preventing overfitting, helps to identify models that perform well on the training data but poorly on unseen data. Model selection, can be used to compare the performance of different models and select the best one. Hyperparameter tuning, helps to find the optimal values for hyperparameters of a model. Considerations. Computational cost. Cross-validation can be computationally expensive, especially for large datasets or complex models. Data shuffling, randomly shuffling the data before splitting into folds can help to reduce bias. Nested cross-validation, can be used to evaluate the performance of models that involve inner loops, example hyperparameter tuning, by performing cross-validation within the inner loop. 7. Machine learning, AUC, ROC curve. AUC ROC, area under the receiver operating characteristic curve, is a crucial evaluation metric in machine learning for binary classification problems. Here's a brief overview. AUC ROC measures the model's ability to distinguish between positive and negative classes. Plots true positive rate, TPR, against false positive rate, FPR, at various thresholds. AUC represents the model's performance, ranging from 0, random guessing, to 1, perfect classification. ROC curve. True positive rate, TPR, versus false positive rate, FPR. Ideal curve, top left corner, high TPR, low FPR. Random guessing, diagonal line, AUC equals 0.5. Interpretation. AUC equals 1, perfect classification. AUC equals 0.5, random guessing. AUC 0.7, good model performance. AUC 0.6, poor model performance. Python libraries for AUC ROC. Scikit-learn, sklearn.metrics.roc_AUC_score, sklearn.metrics.roc_curve. TensorFlow, tf.keras.metrics.auc. Best practices. Use AUC ROC for binary classification problems. Compare AUC ROC across models and thresholds. Consider other metrics, precision, recall, F1 score, for imbalanced datasets. Remember, AUC ROC is a powerful metric for evaluating binary classification models, but it's essential to understand its limitations and use it in conjunction with other metrics. Machine learning, K-nearest neighbors, KNN. K-nearest neighbors, KNN, is a simple yet effective supervised machine learning algorithm used for both classification and regression tasks. It operates based on the principle of similarity is proximity. How KNN works. K-selection, choose the value of K, which represents the number of neighbors to consider. Distance calculation, calculate the distance between the new data point and all training data points. Common distance metrics include Euclidean distance, Manhattan distance, and Minkowski distance. Neighbor selection, find the K nearest neighbors to the new data point based on the calculated distances. Prediction. Classification, assign the new data point to the class that is most common among its K nearest neighbors. Regression, calculate the average value of the target variable among its K nearest neighbors. Advantages of KNN. Simple and intuitive, easy to understand and implement. No training phase, no explicit training is required, the algorithm learns from the data during prediction. Versatile, can be used for both classification and regression tasks. Non-parametric, doesn't make assumptions about the underlying data distribution. Disadvantages of KNN. Computational cost, can be slow for large datasets, especially when calculating distances for all training points. Sensitive to outliers, outliers can significantly influence the predictions. Curse of dimensionality, the algorithm can become less effective in high-dimensional spaces. Choice of K, selecting the optimal value of K can be challenging. Applications of KNN. Recommendation systems, suggesting items similar to a user's preferences. Image classification, identifying objects in images. Pattern recognition, detecting patterns in data. Anomaly detection, identifying unusual data points. Tips for using KNN. Feature scaling, normalize or